basically,
Oh, We got a lot to cover. Anthony, how you doing?
I'm doing good today, sir. How are you?
Not too bad. You got any questions, anything?
Not today.
Okay, cool. Um, if you didn't hear, I put a little cheat sheet on the week 4 at the bottom for this week's midterm. So check that out when you get a chance. It'll help you out to figure out what's going to be on the exam.
Got it. Thank you.
You're welcome. All right. Get going. All right. All right. Always late, so I don't think I'll show up. All right. So, you got any questions, Bianca? No, you good? Okay. All right. So this week we're gonna discuss discrete poverty distributions. And basically it's the same concepts we've been looking at, except that when we talk about discrete poverty distribution, we're really talking about things that have a limited number of outcomes, right? Like if you flip a coin, there's only two possible outcomes, right? So it's discrete. But there's also situations where you have a situation where you're looking at the probability outcomes of something that isn't necessarily it's discrete, but you also need to look over it over time. Like how many people are gonna come to a movie theater? Well, what's the probability people are gonna show up for this movie, right? Over the next day or however long it's in the theaters, right? So we have two different distributions we look at. We look at what we call a binomial distribution, which is basically discrete. It's either one or the other, success or failure, all right? And we look at what we call the Poisson probability distribution, discrete distribution, which is really looking at the same thing but just over time, right? Or over an area, right? You can look at it, use it for space and that kind of thing, right? How many people are likely to come into this room or fill this room up, or how many, what's the likelihood of this room getting filled up, right? Or the probability, right? So we're gonna look at those two things this week. And there's a lot of formulas. So just get ready. We'll try to go through them as slowly as possible. I'm gonna go slide by slide. I'm not gonna deviate too much from the slides this week. Just because there's a lot of stuff and I just want to make sure you guys get it. I want to make sure you guys understand the difference between the binomial, the Poisson, and then what they call the hypergeometric also. And that's basically when when you do research, you can do research when they call it with replacement and without replacement. All right. And so with replacement means that if I look at something and I take it out to look at it, I put it back in. All right. So the chances of it being, you know, selected again are possible. But without replacement, I look at it, I don't put it back in. So now the chances of it being selected are zero, and also the probability for something else to get selected increases, right? So the probability changes with that. So you use the hypergeometric. Don't use it very often, right? It's not something that you use very often. You mostly want to focus on the Poisson and the binomial. Okay. Say something real quick. I need to get something.
So you said if you do with replacement, if you take any recipe back in for the chance of getting it again and without replacement.
Yeah, put your name on it. Yeah, with replacement, right? You could use the Poisson or you could use the binomial. Without replacement, normally use the hypergeometric probability, right? And we'll get into all that. The hypergeometric, I'll just glance over because again, it's not something that's really used a lot. There's other different ways to kind of calculate things, and so we don't really get into too much into that. And for the most part, you're gonna put it into a computer, because there's a lot of factorials. And so you're gonna put it into a computer and the computer will figure that out for you, right? Okay, so, just some, kind of just a introduction, type stuff so when you look at some of this probability, discrete probability distributions, this is kind of what it's used for in business, right? This young lady, Ann Jones, manager of local Starbucks, right? She wants to know, calculate the expected number of visits from a typical Starbucks customer in a given time period, and calculate the probability that a typical customer visits the store a specific number of times in a given time period, right? She's trying to figure out, okay, how much staffing she needs. If she has too much staff, it's gonna cost her money, right? Because you got people sitting around not doing nothing. If she doesn't have enough staff, then people are gonna be waiting too long and they may not come back, right? Bad customer service and that kind of thing, right? So she's trying to figure out, okay, how am I gonna do this, right? Because Starbucks is closing 500 stores, right? She's worried about how's that gonna affect, right, her business, right? How's that gonna impact her business? All right. Okay, so random variable, right, is a function that assigns numerical values to the outcomes of an experiment. Captures uncertainty, summarizes outcomes of an experiment with numerical values, right? So basically, when we talk about a variable, we're just talking about something that's representing something else, right? So the variable can be X, which is normally what it is, right? And that could be anything, okay? But in math, or well, as we're doing the statistics, it's just easier to work with than whatever it is you're looking at, right? When we start figuring, okay, what X is as far as the data point, then we'll plug those numbers in, right? Discrete random variable assumes a countable number of distinct values, okay? Again, discrete, the best way to understand discrete is that it cannot be broken up without losing its function, all right? Just like the example I gave first class, right? If you take a car, you split a car in half, you don't have two cars. You got a broken car. Okay? So a car is discrete. You're discrete. Right? We are discrete. Right? We can't split someone down the middle. Okay? So those are discrete. Continuous is different, right? Continuous could be our weight. Even that can be discrete, but continuous can be our weight. Continuous is it goes on and on and on, never stops. There's no end to it. Okay? So we're looking at discrete probability distributions. And all we're looking at is for that value that we have within a data set, what's the likelihood of it occurring, right? There's a 50% chance that, Angel's gonna walk in here now. There's 20% chance that Jason's gonna walk in here at this point, right? We're just looking at how is it distributed and we can graph it to see what's going on, right? The distinct values represented by X1, X2, L, and Xn, right? Don't worry about the L right now. We'll get into that later, okay? Example number of employees, a continuous random variable is characterized by an uncountable values in an interval, okay? So basically, it just goes on and on and on, right? Return on a mutual fund. You can have 15% return, you have a 20% return, you can have a 30% return, 300% return, you can have 299% return. There's no real way to figure that out. You got 298.5% return, right? It's just not, it can be broken up and still function the way it needs to function. Okay. Every discrete random variable associated with a probability distribution, all right, called the probability mass function. So it doesn't matter what you're doing, just like we had, something like this, right? Before. That's not gonna work. Can't do this, right? Oh, maybe it's the dark one. Something like this, right? 4 equals A, 3 equals B, 2 equals C, 1 equals D, 0 equals D, right? You can graph this, right? Zero, 1, 2, 3, 4. Okay? Boom. 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 Okay? So what we're looking at is the distribution. Okay? How is it distributed, right? And so you can do it that way. You can also do a table, right? Where you have A, B, C, D. And then you have how many people, right, got A's, 2. How many people got B's, 3. How many people got C's, 4. How many people got, and then what's the likelihood, right? What we're looking at is what the likelihood is of somebody getting an A, right? So there's a probability of 0.10, right? Of getting an A. There's a probability of 0.2 getting a B. There's a probability of 0.5 getting a C. So that's 5, 6, 8, and there's a probability of D 0.2, right? Don't forget, the probability distribution always has to equal up to 1. All right, it's always equal to 1. No matter what the probabilities are, they always need to equal up to 1. So I have a 0.10 probability of getting A, 0.2. So these are my probabilities, right? Probability, right? And then these are my events. 3, 4, 5. Okay. So pretty straightforward with that. All right. So that's all you're doing really, is just trying to figure out, okay, how is the probability distributed? So you can figure out, okay, like, what are the chances of me of this happening? What are the chances of that happening, right? What's the chances of me getting, less than, what's the chance of me, just the 2 of you just being the only people coming to class, right? Well, it depends. How many people normally come to class, right? How often do you come to class? You guys regulars, like as far as consistency, right? So all those things would factor, right? And I would determine the probability of the independent events first, and then I would use the rules, right? The addition rule, the multiplication rule, whatever rule I need to use, but there's different rules here because we're using a lot of factorial, a lot of permutations, combinations, and that kind of thing, right? But mostly factorial, right? I'll leave this up for right now in the system. Right? Okay, so the probability of each value of x is divided between 0 and 1. Okay, so just like I said, it has to equal up to 1, right? Any probability we have, right, it's always going to equal up to 1. Doesn't matter. There's a 50% chance of raining. That means there's a 50% chance it's not going to rain, right? So you always have to remember that it's always 1 or 100% or whatever the case may be, but we stick to 1. The sum of the probability equals 1, or the sum of the probability of x equals 1, right? So in this, and keep in mind, like, these are just theorems, all right? They're just formulas. So what you want to do is try to understand what they're saying, right? The probability of x, right, is equal to x. So it's basically saying whatever this x is, it's the same x as if it was in a theorem, right? So here x could be 5, it could be an 8 or a 4, right? So these two are equal, okay? It's just basically whatever data you're given is letting you know, hey, these are equal, so you can use it instead of using the x, you use whatever x they assign you. Okay. Discrete random variable can be also defined in terms of cumulative distributive function. Okay, so we can basically figure out the distribution by cumulatively adding everything up, right? So here we have independent probabilities, right? We roll the die, and every number 1 through 6, right? One has a 1 out of 6 chance of getting selected. 2, 1 out of 6. They all have the same chance of getting selected. Okay? This is saying the same thing here. X is less than or equal to 6, right? Well, cool. All right. What's the probability of x being less than or equal to 6, right? Well, if x is 1, it's still 1 out of 6, right? But what if x is 2? Right? If x is 2, then I have 1 and 2 being my possibilities of not being selected, right? So that means I have a 2 out of 6 chance of selecting a 1 or a 2, right? Same thing here. If x is 3, right, and I'm saying x is less than or equal to x, right? I'm saying that, hey, everything up to 3, I have to count, right, to get me the probability I'm looking for. So if I roll the dice, and what's my chance of getting something that's 3 or less than 3? 3, 2, 1, right? So it's 3 out of 6. You have 3 opportunities to meet the criteria. Okay, so this is just a cumulative distribution, right? We're just adding it up as we go, right? And getting us still to the 1. if you add all these up, it'd be the same thing as this, right? You get one, okay? So understand that when you roll a die, right? For those of us that go to Vegas, right? You roll a die, all right? There's 1 out of 6 chance of that number popping up for you, all right? Or if you got 2 die, right? There's 2 out of 12 chances, right? It still what reduces down to 1 out of 6. Okay, so it doesn't matter at the end of the day, right? 2 die, 1 die. The whole point is to understand that you're trying to figure out, okay, based on my finite set of outcomes, what's my chances of it hitting or getting the number that I want or the probability that I'm looking for, right? Whether it be, what are my chances of getting a 90 in the class, right? What are my chances of winning the lottery or something like that, right? It's a finite number. Well, actually, it's not a finite number, but you guys get the gist. All right. So, okay. This is the same thing, except this is how it's written mathematically, okay? The probability of x equal 1 out of 6, 0, right? So the way you read this is the probability of x equals 6 is 1 out of 6 if x is equal to 1, 2, 3, 4, 5, 6, right? Notice those are all the possible outcomes that you have, right? Otherwise, there's no chance, right? If it's not one of these numbers, then there's no chance of it hitting ever. You understand what I'm saying? Okay, so you got to be careful, right? Right now, if we're using 1 die, that's one thing. But what if we're using 2 die? This would change. Okay, this will change. So, but let's just keep it simple for right now, right? And this is what we call the domain. Okay, this is the domain. And so if you see, if 6 equals 1, 2, 3, 4, 5, 6, this here is the domain. Within the domain of this probability, as long as it's 1, 2, 3, 4, 5, 6, there's a 1 out of 6 chance of getting it. If it's not that one of those numbers, there's a 0% chance of getting the probability of hitting that number or getting that number. All right. All right. Let's jump into a little action here. Random variable discrete probability distribution, the number of houses a realtor sells in a month. Okay. So first thing is this a valid probability distribution? Okay, is this a valid probability distribution? What's the first thing you think we should do here? Take a shot. Take a shot. No such thing as a wrong answer here.
Would we convert the decimals,
Um,
like into over? So they're wholes?
no, because we wanna work in decimals and probability, right?
To get to 1.
So 1, yeah, we want to keep it. I mean, at the end of the day, it doesn't matter as long as you understand that it's a 1 or it could be 100, however you want to do it, right? But it's easier to work in decimals. That way it doesn't throw anything off. As far as the numbers, you don't have to convert back and forth and do math, right? But the question is this a valid probability distribution, right? Don't forget the distribution, right? Needs to equal to 1, right? So if you look at the probabilities, right, for each possible outcome, right, do they equal up to 1? Does this equal up to 1? If you add up all these decimals? Yes. Equals to 1, right? So yes, it's a valid probability distribution because all these particular outcomes, these are the chances of them happening, right? It has to be 1, right? It could be less, it could be less, but it wouldn't work, right? Because then we'd have something just out there like, okay, it's 0.2 or whatever, right? With nothing assigned to it. So this is probably this is good, right? Now, what is the probability that a realtor does not sell any houses? What do you think? 30. 30? Okay, maybe. Okay. So what we want to do is, all right, look at the number of houses, right? So 0. Okay. So x would equal probability of x equals 0 is 30, right? But we need to also figure out, right? Here, okay? That's yes. Boom. We're good here, right? Okay, 30. Now we go to this one. What's the probability that the realtor sells at most 1 house? 50? Okay, now make sure you read the question, right? What's the price to sell retailer sell most one house? Right? So why you say 80?
Actually, I know I messed up, actually. I was thinking because you just add 30 with the 50.
Yeah, no, that's right.
Oh, okay.
Right? Because you have to include that in the domain, right? Because there's a pop to get to one, you gotta get through zero first, right? There's a starting point. So she could not sell any houses, but she could sell one too, right? So what's the probability of no houses? 0.3. What's the probability of one house? 0.5. All right. You add those two together and you get 0.8. Okay. What's the probability that the retailer says at least two houses? Okay. Now, pay attention to this, right? Sell at least two houses. What this is saying is equal to or less than, right? So make sure you write it correctly, right? Or greater than. Well, no, yeah, greater than, excuse me. So X is greater than or equal to 2. Okay? So yes, ma'am.
You said greater than?
Yeah, it's greater than. Yeah. X is greater than or equal to 2, right? So the probability of X equals 2 plus the probability of X equals 3, right? 0.15 plus 0.05 equals 0.20, right? So for D, what is the probability that the realtor sells at least two houses? 0.20, okay? And then it's actually to graphically depict the probabilities in the houses sold. Pretty straightforward here, right? Probabilities on the left, on the y-axis, on the x-axis, number of houses sold, okay? And you just graph it, point, where they intersect, where they meet, and you just, there you go. All right, so, okay. When we go back here, right? Let me make sure. Good, okay. All right, everybody get a general understanding of what's going on? Okay, all right, because this is gonna get a little harder from here. All right, so, yeah. So I want to make sure you guys have this understanding here of that, hey, probability falls between 0 and 1, right? The sum of probabilities equals 1, but discrete random variable can also be defined a cumulative distribution function. But what you're really looking at is, okay, how do I take the independent probabilities, right, to get something I'm looking for specifically, right? And make sure to understand that all these, if you're looking for 6, it says less than or equal to or greater than, all right? Depending on which direction it tells you to go in, you have to either include the things that are before it or include the things behind it, or ahead of it, I should say. All right. So, for instance, in the question it says, "What is the probability that the realtor sells at least two houses?" Right. So, probability of X greater than or equal to 2, right, equals the probability of X equals 2 plus the probability of X equals 3, because you could sell 0 houses, right? You can sell 1 house, right? But they said 2. So you can exclude 0 and 1, right? So basically, I need at least 2 houses. So 2 is 0.15, selling 3 is 0.05. Okay. So when you read the question, just make sure you understand what it is they're asking you for before you run off and kind of do whatever you want to do. All right. Okay. So let's look at the expected value of variance and standard deviation. All right. The expected value basically is just another name for the mean. Okay. What do you expect the value to be based on the probability? All right. So we'll get into an example, but let's just say like you have, $1,000, $2,000, $3,000, $4,000 as bonuses, right? Which is the example that they have. What's the chances of someone getting $1,000 bonus? What's the chance of someone getting a $2,000 bonus? What's the chance of them getting $3,000 bonus, right? That's my expected value, which is the average, right, for the probability distribution. All right, so just remember that. Don't it as E, expected value of X, or the mu, right, which is the population mean. Okay, that's the simple population mean, indicates central location, right? It is calculated as U, right? Mu, excuse me, the sum of X times the probability of X equals Xi, right? Or Xi times the probability times X equals Xi, right? All it's saying is, hey, look, take whatever X we give you, multiply by the probability, right, of the X equals Xi, okay? And then you'll get the mean, okay? But you need to sum up everything that is before it or after whatever the question dictates, all right? The variance is denoted as variance, right? This is a population variance, okay? Nothing, this is a symbology here. Same concept as we talked about last week, variance, standard deviation, mean. They're all the same, okay? It's just that we're doing a probability distribution for discrete probabilities. And so these are the means and the standard deviation for those particular distributions, right? And we're talking about discrete probability. We're talking about something that can only be, it has only two outcomes, right? If you flip a coin, it could be heads or tails. That's it, all right? If you do what we call if you have a situation where you're looking at something over time, but it's also discrete, this uses something different called the Poisson theorem or probability distribution, right? But we'll get into that. Right now, we're just looking at the mean, the variance, and the standard deviation for the probability distribution, discrete probability distribution, all right? So the variance is denoted that way, the variance is calculated this way, deviation is this way. For the most part, you're not going to be doing any of this. Okay, you're not going to be looking for the variance and the standard deviation of these things. You're really looking at the probability, right? Most times they will give you one piece of this info and you can figure out the rest from that. And they'll probably give you the mean, or if not, you know what it is because you know that the expected value X is the same thing as the mean here. All right. All right, so let's do this.
Ask if I can open the door for him.
Yeah. Brad was the owner of a large car dealership in Chicago. Brad decides to construct an incentive compensation program that equitably and consistently compensates employees on the basis of their performance, right? So, first thing he wants us to do is calculate the expected value of the annual bonus, okay? So, what do we think is going to be the annual bonus, okay? Just in general, right? And so, how you want to do this is basically you go back to your formula, right? The expected value is the sum of xi, which is whatever x is given as a data point, times the probability of x equals xi. Well, that was quick.
Yeah, I didn't even have to go down. Somebody.
Okay, somebody got in. Going on. So we go back to the formula and say, okay, I'm multiplying xi times the probability of x equals xi, right? So basically what I'm looking at is these are my xi's here, okay? And these are my probabilities. Okay? And so what I'm going to do is I'm going to multiply each one by its corresponding probability, and I'm going to add them all together. Okay? After I multiply each one, I'm going to add it together to get my expected value, right? Because that's what this formula is saying. This formula here is saying. If you want to know what the mean is, you sum the data point times the probability of x equals xi, right? And don't forget, x and xi are the same. It's just you gotta wait to see what xi is, right?
Mhm.
So xi is this, same thing as x, right? Okay, so calculate the expected value of the annual bonus. So based on the formula, what are we gonna do? What's the first thing we're gonna try to do?
It's the sum of the. It's the sum of the multiplication of those, right?
Mm-hmm. Yeah.
So you have to multiply each one.
Right, so, but for the first question, right, we're gonna multiply 10 and make sure you read the caption too, right? Bonuses in $1,000 increments. All right, so this is really 10,000, that's 6,000, that's 3,000, and that's 0,000. Okay, no money. All right, so we'll just leave it simple as 10, all right? Multiply by what?
0.15.
0.15. What does that give me? Anybody?
1.5.
1.5, okay? 6 times 0.25,
6,000 times 0.25, right?
6, just 6.
I
One
thought you
point
said
five.
it's thousands.
It is, but we're gonna leave it just for simplicity's sake, we're gonna leave it the way it is.
Oh.
Yeah, we'll leave it the way it is. You can do it that way, it doesn't matter. It's gonna give you the same answer.
Oh.
It's gonna give you the final answer, it doesn't matter. Because math, addition and multiplication are cumulative.
1.5.
Okay, 1.5. Okay, what's the next one? 3 times 0.4, right?
1.2.
And then what's the last one? 0 times
0.
0.2, right? Okay, and that gives you 0, right? So what you do, you add all these up. Right? 1.5, 0.5 gives you 3. Bring that down to here. That gives you 4.2. And we have a 0, so nothing. So 4.2. Okay? So our mean is 4.2, or our expected, excuse me, x is equal to u, which is equal to 4.2. Okay? So 4.2. Now, if you want to convert it, now what is it?
4,200.
4,200 is my expected value, okay? So if, for the most part, if I go off these probabilities, I'm expecting to pay $4,200 whoever gets a bonus, all right? Calculate the variance and standard deviation of the annual bonus, all right? So now we need to go back to the formula again. The variance is denoted as the variance squared, okay? The variance is calculated as the sum of the xi minus the mu squared times the probability, all right? We're not gonna do all that, okay? I'm gonna show you because there's another diagram, right? But when you are physically doing the problems, you need to be able to understand that that's the formula you need to use, okay? So the variance, boom, this is the formula for the variance, all right? And remember, this is just the symbol for population variance, all right? So population variance, right? And then we got this formula here, same thing. Add up everything 10 minus, or whatever you get, 10 minus the mean. What is the mu? What's this number?
4.2.
4.2, right? Squared times the probability of whatever x is, right? Times 0.15. Right? Because don't forget, all this second part is saying is, hey, what's the probability of x equals xi, right? We know that x equals xi is 10, right? In the first situation, it's 6 in the next, 3 in the next, and 0 in the next, right? But x and xi are equal in whatever we have up there, right? So the probability for that first one, right, is 0.15, right? So we would put that there. And then we would take the 10 minus the 4.2, square that, multiply that by the 0.15, and that would give us our variance, right?
Do that for each one.
Yeah, you gotta do that for each one, right? Same thing, right? You always have to do it to each one. So the way we got the mean here, we'll get the variance same way, right? It's just a little bit, an extra step, but same thing, we'll add it up at the end,
Okay.
okay? And the standard deviation is just the square root of this. Okay? That's it. So remember, if you're looking for the variance or you're looking for standard deviation, and give you the variance, the square the variance.
Are we gonna do an example?
We are, yeah, we're gonna do an example here real quick. Okay? All right. Okay, here's the example, right? So we started with that part. We got the expected value, right? 4.2 or 4,200. Calculate the variance standard deviation of the annual bonus amount, okay? All right, so here's the chart. All right, so here, and I recommend if when you're doing it, kind of do it like this. It makes it easier just to kind of see everything, lay everything out, right? So here you have your xi, here you have your probability of x equals xi. Here you have the xi multiplied by the probability, and then here you have the what you gonna call it?
The standard deviation or the variance?
The variance of the data set. Okay? So you can see 10 minus 4.2, right? Squared, right? Multiplied by the probability of x equals xi, which is 0.15, which we already knew that. Okay, so understanding nomenclature, understanding what each symbol means, understanding, that n is one thing, the variables don't change, is what I'm getting at, right? X is always going to be equal to xi. N is always going to be equal to the number of data points you have in a data set, right? Whether or not it's a lowercase n or uppercase n, that's the only difference, right? In the uppercase n, we're talking about the population. A lowercase n, we're talking about the sample from a population, right? Not a distinction you need to know right now, but it's an important distinction if you're actually going to be doing research and understanding the problem and what they're asking, because the formulas are a little bit different, okay? But for all intents and purposes, we're just focusing on the population right now because we know that it's a discrete population, right? There's only two outcomes, or there's only a limited number of outcomes. So we know that, hey, we've exhausted the whole population. We know exactly what's going on, right? It's not like we're trying to like figure out, okay, well, there's a whole bunch of other stuff out there. There could be different bonuses structured. It could be, we know what it is, right? We know what the mean is. We know what the standard deviation is, or at least we're gonna figure it out, right? So the variance is here, right? We figured out it's 9.97, right? In thousands, okay? And then what we're looking for is the standard deviation. So we take the square root of that, and we get $3,158, right?
Oh, so it says 9.97, then it says and 1,000 squared.
Yeah, in thousands squared. Because this variance here is a dollar amount.
But it's not squared yet, right?
No, it's not squared yet.
Oh, okay.
Yeah,
It's saying,
no, no, it is squared. It's done. It's squared. It's just saying as a note to remember that this is money.
Mhm.
That's all. It's saying once you're done, like once you convert it over, right, then you can do it. Like if you did it in thousands instead of keeping it 1063, you would still need to square.
Okay.
That's what it's saying. All right. So I wouldn't worry about that right now. Okay. Because they convert over here, you see how they go from 3.158 to 3,158, right? Because you're looking for the standard deviation of this data set.
So they just squared 9.97 and got 3.
They did the square root of 9.97.
Oh, square.
Yeah, don't worry about this. All it's saying is that this is that.
Mhm.
They're just reminding you, like, hey, don't forget that this is money. Because what will happen is people put 9.97 and they'll forget it's money. And they won't say $9,970. Right?
We can take off points for that.
Yes. That's an important aspect, right? What is your metric? What is your measure, your unit of measure? Like what are we talking about here, right? I gotta know. So here we're talking about thousands, right? That's why I put it there to remind you, because it's important. All right. Here, all we did was take the square root of 9.97, which is 3.158, which equals to $3,158 right, as the standard deviation, right? Everybody remember what the standard deviation is?
The square root of the variance.
The square root of variance, yeah, but what does it mean? What are we talking about here?
How close each thing is. How
Okay.
far apart it is from the main number.
Yes, from the mean. Okay, I think you were talking about, yeah. How far on average is my data points in my data set away from the mean? On average, okay? So basically, if my one standard deviation is 3.158, right? If I were to graph it, right, on the bell curve, all right, it'd be like something like this. Like we had something like this, right? Remember I did this sexy thing last week? 0, 1, 2, -1, -2, okay? What is our 0?
Mean.
Huh?
Yeah, mean.
The mean?
Yeah.
Yeah, but what is it? What's the physical number? What's the actual number? What's the actual data point?
I don't remember.
You know what it is.
4.2.
What?
4.2.
4.2, right?
Oh,
Alright,
I was just
42.
talking about this
40.
example.
42.
Oh,
It's
okay.
still the same example. Yeah, it's 4.2, right? Like it says up there. The mean is 4,200 or 4.2, right? So now our standard deviation is what?
3.158.
3.158, okay? We'll keep it.
So there's no rounding.
Yeah, you can round. Usually you round to 2 digits unless otherwise specified. So let's just do 1.16, 3.16. Okay? All right. So my one standard deviation is 3.16. Okay? So what's it telling me now? So what if I wanted to know what's the range of my one standard deviation?
You have to find the lowest and the highest number, right?
Okay, how would I do that?
Mm.
Okay. 3.16, which is my standard deviation, plus 4.2 will give you my high end. 3.16 minus 4.2 will give you my low end.
Oh, that's an easy way.
And that gives you my range.
That's an easy way to learn how to do this.
Yeah, that gives you my range now, right? So I know if someone within one standard deviation of the mean, I know that either their bonus is gonna be 7,003, or it's gonna be let me see, that's terrible, 1.04. Okay, so if we translate that, it's gonna be 1,040 to $7,360. Okay, that's my first range. Right, that's my standard based on my standard deviation. Now I've had two standard deviations, right? What would that be? What's two standard deviations?
That would be double.
Double, that's all it is, right? So we're talking about what? 9 point, what's this, 2, 3, 32, something like that? I'm just
Yeah.
guessing, right? Two standard deviations, right? Same thing, always from the mean, right? So if I wanna know what is my range for two standard deviations, right? So I figured out for this one, right? One standard deviation from the mean. All right, now I wanna know what it is from here. Two standard deviations from the mean, right? So again, it's 9.32 plus or minus 4.2. Okay? And then you do the math. 4.2 plus 9.32 gives me give or take 13, right? 9.32 minus 4.2 gives me 5.1 or something like that, right? So 5.1 to 13 is my second range, or 5,100 to 13,000. Okay? That's within two standard deviations, right? Of the data set, of the mean. So basically what it's saying is I've accounted for 95% of everyone that's gonna get a bonus is gonna be between whatever the low is for the first standard deviation, right? It's gonna be between what was it, 2 point?
1.6.
Yeah, it's gonna be 1,600 all the way up to 13,000, right? But I know that's gonna include everybody, 95% of the people within my group, right, within the company are gonna get a bonus between 1,000 and 13,000. Okay? Now, if I go three standard deviations, which is out here, right, same thing, three standard deviations, multiply 3 by this, it gives me, this was not, this is 6.
I was thinking that.
You just said something, you be checking me all the time. 48, excuse me. 48, something like that, right? Okay, so don't mind this is wrong. 6. Okay, this is kind of high.
9.48, yeah.
Yeah. This is needed there. Okay, so no, that's not right. Either way. So every time you do a standard deviation, all you're saying is, okay, this is my range if I'm looking at how many data points are gonna fall within that range. Okay? So the concept behind this is that, as I said, this accounts for 95% of the population. Okay, all this. 2.5 here, 2.5 here. right? Because it's symmetrical. That's the other 5%, right? Which we usually call outliers or just what we would consider statistically significant.
That's 2.5.
2.5, right? Because don't forget, all this underneath here is 100 or 1, right? Since at 2 standard deviations, right, it's considered normal. It's considered, there's nothing special here to look at, all right? Once you start getting into the tails, then we start figuring, okay, maybe there's something that's happening that isn't just coincidence. There's a purposeful thing going on here that's making this happen, right? And that's the interesting part we want to look at, right? We don't care about this because everybody's average, everybody's the same. And I don't care. I want to know why, again, go back to height. Why is Shaq so tall? Right? I want to know, right? I don't care how tall I am because everybody's pretty much my height. It doesn't matter, right? Genetics, whatever, we're all the same. Whatever it is that determines our height, great. But if we have somebody that's super tall, right? We want to know why. Because maybe we want to replicate the height, right? Maybe we want to replicate certain things and, and build a model, right? It's like we build models for hurricanes and everything else, price, or profits, right? This is really where it's gonna come into effect for you guys when you start looking at, okay, what is my profit range? All right? If I have, on average, 5 people come in and I have a standard deviation of 2, right? How many people can I expect to come in at a certain time? Or how many people can I expect to come in general, right? Based on 1 standard deviation, based on 2 standard deviations, right? That gives me an idea, okay, all right, well, on a Friday night between, 6 and midnight is probably the busiest time for a restaurant, right? How do I calculate how much food I'm gonna need? How do I know what people are gonna order, right? How do restaurants do that?
They survey.
You had the servings, right? But how do I calculate that? If I have a special, how do I calculate how many specials I put out,
Average.
right? Yeah, I pick an average, right? But I also have to look at the standard deviation and say, well, just because it's there, some people will pick it out because it's special. Some people pick it out because it might be their favorite thing and it happens to be the special, right? So I have to kind of figure out, okay, what is the correct number of specials I need to have so that when people order it, we have it on deck, right? It'll go back probably to the average number of people we have on a Friday night. And then based on, what it is, depends on, what's the percentage of people that eat chicken? What's the percentage of people that don't eat seafood, right? If it's a seafood special, those kind of things, right? That's how kind of, you'll hear.
Is that how the airplanes do it too?
Yes,
That's why they always got extra food on.
yes,
They always mess up the average.
yes. And all planes when they're selling tickets, right? Every flight you go on is usually oversold,
Wow.
usually, okay? Usually oversold. Because there's a certain amount of people that just aren't gonna make the flight. They're just not. They change their mind, the weather, they're just late, just not gonna make it, right? And then guess what? This is where the standbys come in, right? That's where you got a standby list. But you have an idea, okay, how many people out of this 300 seats I have on the plane, how much of those do I expect not to be filled by people that have purchased tickets for this flight, right? So that's how they figure that out, sort of, right? So you'll use this, and again, you won't do it by hand. Everything is done by the computers, right? Automatically, but you need to understand the concept, and that's why we just do it the way we do it now, right? So
Do it on Excel.
you can do it on Excel, yeah. I would recommend, as you're doing the problems, yes, do them by hand, right? But also go to Excel, put in just to double check your answers, right? I mean, we have different things now, Chat GPT and all that stuff that you can put the problem into and it'll get an answer. So whatever you need to use to double check your answer, cool, and also give you an explanation of, maybe your answer you didn't get the right answer, so you can see the steps, right? And kind of see where you're going. But I can tell you now, being organized is like one of the best things you can do for yourself. And staying ahead of this game and understanding what's going on and understanding what each symbol, what everything means, right? That'd be the first thing I do. I would lay out my variables and see what I have. And then from there, again, what are they asking me? Find the appropriate formula. And then go from there. Okay? All right. So, all right. Now, see, if Brad has 25 employees, how much you expect to pay out, right? So we know that the average payout is 4,200. He has 25 employees. So Brad knows he's gonna pay out at least $105,000 in bonuses. Okay, no matter what, no matter which way he slices it, whether or not he has somebody that's getting $1,000 or somebody's getting $13,000, at the end of the day, it's gonna average out to 4,200 per person, and he has 25 people, so he's gonna pay out 105,000 at least. Okay, so that's pretty much how you run that, right? So you have the expected value, the variance, and the standard deviation all at once, right? And understanding what each formula is looking at, right? You got your data points here, your xi. Don't forget your x is equal to xi. There's the probabilities of each one of these occurring. You got your mean here or your average, right? All it is the xi or the data point multiplied by the chances of it happening, right? You add it all up, right? You follow the formula here, okay? So if you're looking for the mean, that's the formula there. If you're looking for the variance, that's the formula there. You're looking for the standard deviation, which is really what you're looking for at the end of the day. You just take the square root of this, of the variance, okay? So at the end of the day, it's just a big old square root. After right, if we had a smart board, it's just a big square root all over this, like this, boom, square root. That gives standard deviation, okay? But I forget, I put a cheat sheet on week 4 for you guys to help you guys out with the midterm. It's kind of let you know what's on it and what you should be kind of focused on. It's like 15 questions, all multiple choice. So it makes it easier for me to grade and should be straightforward. Okay. Nothing on there we haven't talked about yet. Again, you will not have access to the internet on the computer you're using. Okay, there's a new system in place. I think it's still used in a place where the system, once you enter the exam, it blocks the internet. Okay, so you can be on your phone, you can do some other way, right? Which I don't, I ain't telling you to do that because this is dishonest, right? So, but at the same time, I'll know because it's gonna take you longer to get through on your phone and to do it and all that stuff, right? So my suggestion is to basically write down all your formulas on a little piece of paper or print it out, however you want to do it, and just have it next to you. And then as the questions pop up, just, okay, cool, this is what it is. All right, pick the right formula. And the formulas are relatively the same for the most part across the board. All right. This is a little different just because it's discrete and we're using more factorial. We'll get into it, but we're using mostly algebra, but some factorial in here, permutations and stuff like that, because we need to know what the different combinations are. All right, we need to know, okay, what are the chances of me getting 1, 2, 3, 4, 5, 6, or a combination of those particular numbers, not in any particular order. I just need to know what are my possible outcomes, right? If I'm playing the lottery, what are my chances of winning the lottery, right? 1 in 15 million or something like that. I can't remember what it is, or 154 million, something like that, right? The odds are totally against us to win the lottery, okay? But at least you know what they are, right? When you go in, you're going eyes wide open, you buy a ticket, good luck, okay? All right, so pretty straightforward here with the expected value, variance, and standard deviation. Don't forget, the expected value is the same as the mean, okay? And the x and the xi are the same thing. Mhm. All right, what is this now? Okay. Risk averse consumers demand positive expected gain as compensation for taking risk neutral, and then risk level. All right, there's different risk levels in business and life. Okay, some people are risk averse, right? Bianca says she doesn't go to Vegas and gamble, right? She's risk averse. right? She likes to keep her money in her pocket, right? Me, I'm risk loving, okay? I go to Vegas, I got a budget, and I'm going to the table, and I'm gonna take my chances. If I lose all my money, so be it, right? But I know there's a chance of me losing my money, right? Risk neutral customers are like, hey, I'll do it, but what's the return? Like, is it worth? Is the squeeze worth the juice, or the juice worth the squeeze, or whatever they say, right? Is it worth it to me, right? To take that type of risk, and I'm gonna get this reward. It may not be enough for you, right? You may be like, you know what, yeah, it's cool, but if I'm only gonna get this, then I'm taking a really big chance. I'm good, right? So again, just keep that in mind because that's really, if you guys want to finance, is what you're gonna be dealing with all day. Risk. Okay, finance is nothing but risk. Am I gonna risk a certain amount of money to do this? Am I gonna, opportunity cost, right? Am I gonna do this instead of that because it's gonna yield me a high return? But I'm still taking a risk because I may miss, a lot of people are very fearful of missing the AI trend, right? Of being left behind with AI, right? So right now, everybody's pretty much risk loving consumers, right? Because we have no certainty that AI is going to do anything, right? There's no guarantee. We're just hoping that it's a technology that really innovates and changes things up, right? But we're not really sure, right? So everybody's kind of risk loving right now, right? Especially with the state of the economy, our social structure, like the way the way society is going right now, all the conflicts we have, there's a lot of risk that's being taken, a lot of chances people are taking, right? In the hopes of big rewards, right? Bigger the risk, the bigger the reward. All right. Okay. Here's another example. Suppose you have a choice of receiving $1,000 in cash or receiving a beautiful painting from your grandmother. All right. So pay attention to the wording, right? Suppose you have a choice of receiving $1,000 in cash or receiving a beautiful painting from your grandmother, right? So you can see that it's discrete in nature, right? It's only two outcomes. You're either gonna take the money, right, or you're gonna take the art. Okay, so that way I know, okay, I'm using either binomial or Poisson theorem or formula, right? Because it's discrete probability distribution. It's not like the other ones where we conditional probability, right? What we did last week, right? Intersection, union, right? It's some of it, there's fundamentals of those things in there. But here we're looking at, okay, a very specific number of outcomes. Either it's over time, which is Poisson, or it's just limited to, hey, yes or no. That's it. Flip the coin, heads or tail. All right. There's only two outcomes. All right. So the actual value of painting is uncertain, right? What should you do? All right. So we have our X's here, right? On dollar amounts of how much we think the painting could be worth, and what are the chances that the painting is worth that much. Okay. So we have our X, we have our P, X equals XI, right? Or we just leave it X because they didn't use XI this time. The expected value is 1,050. Expected value is greater than 1,000. It may seem logical to choose the painting, but a risk-averse person might not agree, right? Okay. So if I know the expected value is 1050, right? And don't forget, the expected value is what?
The thing right there.
The mu, right? The mean. Okay, the average. Okay?
The mu.
The mu, it's called mu, right? When we're talking about the population. If we're talking about the sample, it's just the mean.
Okay.
Okay? They're both the mean, but it's written differently. That's it. Because remember, the mean for a sample is what? Anybody
The
remember?
lowercase n.
No, the lowercase n is the number of data points in your data set.
So the
That's
circle-
right there,
Which one?
that one right there.
No, this is standard deviation. It's not on here.
Okay.
No, it's not on here
That
though.
one right there.
This is it, right? But this is for population.
Yeah, that's mu.
That's a mu, yeah.
Okay.
That's for population. This is for a sample. X bar. Okay? So it's important that you understand the difference, right? As a note, remember I said, if you see a Greek letter or Greek symbol or capital, it's more likely talking about the population. If you see lowercase and just lowercase letters and not Greek letters, then it's probably talking about the sample. okay?
It's the same formulas for.
Yeah, for the most part, yeah, it's usually the same formulas, yep. But we're using mostly Greek letters here because we know what the population is, right? We know what when I say population, we know what the outcomes are. It's either one or the other, right? So we know what the population of outcomes is, okay? So expected value is 1050 or 1050. Expected value is greater than 1,000. It may seem logical to choose the patent, but a risk-averse person might not agree. All right. So we got our probabilities here, right? All right. Oh, they don't do it. No, this is an example. All right. So if you were to try to figure out what the chances are of you deciding whether or not you want to do it, right? You would just take that, multiply by that, right? And then use the mean formula, and after that, use the standard deviation formula, right? Or the variance formula to get the standard deviation. And you can figure out, okay, what are the chances of me deciding to take the payment or decide to take the money, right? It tells you here the expected value is 1,050 is greater than 1,000, right? So you got 50% chance here. So it's greater than 1,000. Why would you not take the money, right? Okay. Well, actually, why would you not take the painting over the money? Because the expected value is 1050, right? But that might not be enough for somebody. You guys ever seen the game Deal or No Deal?
Yeah.
Right?
I love
When-
that game.
When they say, pick a suitcase or briefcase,
Oh, I see.
you know what I'm saying? That's all probability. What are the chances that the $1 million is sitting in that suitcase? Right? Because the $1 million is there, right? It's a perfect discrete probability distribution problem because there's only a certain amount of briefcases, and there's $1 million thing in there. Right?
So isn't the expected value based on what people are trying to pay for it? For example, it is 1050, but the market's whatever, $800.
Yeah. But I mean, if we were really thinking about it, yeah. But this is just an example, right?
Okay.
But that's something that in real life, right? It's all subjective, especially when it comes to art, right? What's what's good to you may not be good to somebody else, right? So people pay billions of dollars for Picasso, great, but it's very much a subjective thing, right? We've given it value based on the fact that we think it's important. Like anybody familiar with NFTs,
Yeah.
right? Non-fungible tokens, right? NFTs were a big thing a couple of years ago, right? I think Justin Bieber paid what, $15 million for one of some crazy nonsense like that. How much is it worth now?
Nothing.
Nobody.
Nothing. Nothing. The NFT's worth nothing, basically. Right? He took a loss on that, right? Again, subjective value, right? Because we were told it's valuable and people were clamoring for it, right? The demand was there. That's what creates the value, it's the demand. That's why, when it comes to marketing, right? These numbers, all this stuff is important when it comes to marketing, it's all psychological, it's all mental, right? If I tell you, I could say the same thing, right? These are both the same thing. But guess what? I put a little Louis Vuitton symbol on here. And this one is from Walmart. It all perfect example, which is real life, right? You guys been to Costco before, right?
Yeah.
Kirkland,
Yeah.
same thing as Grey Goose. Same thing as Tito's. No difference. They come from the same place, literally come from the same place. Okay? But guess what? You're gonna pay more for Grey Goose. You're gonna pay more for Patron or whatever it is, right? When you can get Kirkland, all they do is put another different label on it. I promise you. Okay, no difference, right? So the value is created that way, right? Because someone said it's valuable, right? That's why it's important. If you start your business, you should always put a premium on it. Because
And brand ambassadors and influencers really, because just like you're saying, it's valuable because people say it.
yeah, people say it, right?
It's the same thing with diamond.
Yeah,
When you want
exactly.
to get engaged, it's most expensive thing ever. But when you want to resell that,
No,
you
it's
get
different,
nothing-
right?
You get nothing.
Yeah,
out of
you
it.
get nothing out of it, right? But just, as a side note for us fellas that are looking for diamonds, if you go out to Kentucky, there's a city in Kentucky, it's in the woods, right? You can go out and pick your own diamond. Not pick it, but you gotta go look for it, right? But there's diamonds all over the place. You just gotta dig for them, right? It's unfinished. It's not, but you can find a diamond out there, take it to a gemologist, and they'll hook it up for you.
My family's been doing this jewelry business for a long time.
Oh, yeah?
It's like 1700s, so we
Yeah.
got a lot of stories and stuff. I'm into this stuff too, so.
Mhm.
I tell people, I'm like, hey, United States, GIA is a monopoly.
Yeah.
As compared to the rest of the world. You go
Absolutely.
buy the same diamond from Israel.
Yeah.
It's gonna be less than half the price, and it's the
Easily.
same thing, but GIA is GIA.
Yeah, it's GIA, it's the Harry Winstons of the world, right? Keeping diamonds and all that stuff you see in the movies about them having diamonds in these lockers. It's true.
It's safe, yeah.
They have them in the safes because they need to control the market.
Right.
Right? If I can walk out and kick a rock and it's a diamond, what I need your diamonds for? All right? I have to create value. So guess what? Lock all that diamond up. Yeah, I know it's a 10-carat diamond. Yeah, I got it. We're not selling that. Put that away,
No,
bro.
no, they don't.
Put that away.
Yeah.
We're not selling that
They don't
today.
talk about the price in the market too.
No, they don't talk
If
about
you
the
go
price
to
in the
one store,
market.
ask them, the other store is not gonna tell you what the
No,
price
yeah,
is.
they're not gonna tell you what the price is, right? So all this stuff is subjective to certain when it comes to art and that kind of thing, right? But everything's really subjective, right? At the end of the day, when you're trying to figure out, okay, how do I buy a house? How did they buy a house back in the day?
They built it, about plot.
They built it, right?
Yeah.
What if you didn't build a house? What if you couldn't? What if you were a carpenter? What if you were like me? I can't build no house. What do you do? What did they do?
Buy it from the market.
Maybe, but what else did they do? What did they really do back then? What was the system of commerce back in the day? How did people transact with each other?
They like trade and stuff.
Banks.
Barter.
Yeah.
Before banks, they were bartering, right?
Yeah.
Because we didn't have a unified monetary system, right? Everybody had their own money. Okay, everybody has their own money now, but at the same time, people didn't really understand, like, okay, how do I take Chinese money and take it back to Italy and spend it? There's no bank or nothing to change that up, right? So basically, it became we're bartering locally, right? Okay, look, I'm a doctor. I can't build a house, but I need a house. So guess what? I give you a year free medical services if you build my house. Right? That's how they did it back in the day, right? They bartered, they exchanged services and that kind of thing, right? So again, subjective, right? Okay. All right. What time is it?
10:44.
Okay, cool, real good. Um, everybody's familiar with portfolios and investments and that kind of thing, or does anybody need? Nobody? You guys don't invest?
I'm really
I do.
about to invest in the food.
You do? You don't? Younger? Invest? Who got a 401k here?
I don't have one because the dividend's at 28%. It's bad.
Got a TSP.
I don't got.
TSP works. Okay. What do you have?
I do through Robinhood, but I just stopped recently. The bank sent me a W-9 form saying that you're earning dividends and you need to pay 28% on dividends and all that.
Yeah.
Like,
Yeah, depends what you got though. If you got a dividend bearing
yeah, what's
instrument.
it called? What's this?
Yeah, QQQ or Vanguard or
No, it's Robinhood. It's Hood, Robinhood.
Robinhood pays out a
Yeah,
dividend.
Yeah.
Oh, interesting. I didn't know that. Okay. Either way, all right. I recommend you understand investing, right? And how to invest and what happens to your money, compound interest and all that stuff. Because that's really how you grow your money, right? If you're not buying real estate, which is really not a guarantee anymore about, accumulating wealth, it's about investing. It's about getting into the market and understanding the dynamics of it, right? Because even if you go out and you open your own business, that's an investment that you're making, right? The cost of capital, the cost of raising capital, the weighted cost of capital, right? Liabilities, all these things that you got to think about, like, okay, where's this money coming from? All right. Am I getting it from a line of credit? Am I getting it from my revenue? All right. How am I expanding? How am I growing? All right. Am I getting investors? All right. That's a whole nother ball game, right? And getting people invest in your your project or your company and letting them know like, hey, you're not in charge of anything. You just have a stake in the business. All right. But either way, all right. So when we talk about portfolio, we talk about a collection of stocks and bonds, right? Most people have a broker that they use, whether Charles Schwab or JP Morgan or whatever the case may be. Nowadays, it's possible to do it like Chase and do Robinhood, right? I have Robinhood. I use it to do my thing. I had E-Trade back in the day. I still have it,
Did
right?
you buy the stocks before they went up crazy?
Which one?
The Robinhood stocks.
No, I didn't buy Robinhood stock. I just used the app.
Well, it went up real bad, real up.
Yeah, I'm sure. Yeah, they're doing well. They're doing well because what Robinhood's providing a service that most of us didn't have access to. You can invest like this 10, 15 years ago.
It's really simple now.
Yeah, you had to go find a broker, pay commission, pay fees, and a lot of times the brokers would do what was in their best interest to make as much fees and commission off of you, right? They wouldn't pick something that was gonna make you money. They pick something that's gonna make them money, right? It's still like that to a certain degree, but it's changed a whole lot because you understand that now we have options. You can go to Robinhood and plan out your whole retirement and manage it yourself, right? And that's what I always recommend. You go in and you start, even if you start $25 a month in a mutual fund or a Roth IRA or something, right? Get involved in the market because your money's going to grow, right? If you understand the market, right? And it will work for you while you're sleeping. That's the best type of money you can have. You're making money while you're asleep. You're making money while you're on vacation. You're making money while you're doing nothing, sitting on the couch watching Netflix. Okay, that's what you're looking for, right? So, so a lot of times the guys are using this kind of stuff to figure out return on assets on particular instruments or whatever they call, whatever it is. All right. All right. So portfolio returns. We'll just go over this real quick. All right. Expected value of X plus Y is equal to the independent expected value of X plus the independent expected value of Y. Variance, same thing, X or Y. Independent value variance of X, independent variance of Y, and then plus 2 times the covariance of X and Y, right? Where co is the covariance between X and Y, right? So we're talking about covariance, we're talking about their relationship, right? Correlation. How they aligned, right? How is one behaving when the other one does something, right? Because it's going to have an impact on whether or not your stock goes up or your stock goes down, right? So for instance, everybody from NVIDIA,
Yeah.
right? NVIDIA just had earnings today, right? It happened after the market closed, right? Huge profits, right? Now, tonight and tomorrow, when the market opens, you're gonna see that in the market.
Oh, fly.
It's gonna,
Yeah.
it's gonna be green. It's gonna buy. It's gonna shoot up more than likely, right? But you still gotta watch it because sometimes the market's weird and does funny stuff, and it may go against you, right? But at the end of the day, right? When we look at the covariance, we're looking at okay, if NVIDIA is up, and NVIDIA, it's important about NVIDIA because if you look at, and this is a little maybe too much, but if you look at NVIDIA and understand the market, NVIDIA is one of the major players in the tech sector. And one of the lead indicators as to whether or not AI is really like something that's going to hold, right? Because based on the amount of chips and things that people are buying from NVIDIA, you can tell whether or not there's a real interest or not, right? If they're selling $1 billion worth of microchips and transistors, right? Okay, people are really trying to do this AI thing. But if they only sold $1 million of transistors or microchips, they're like, nobody really worried about no AI, right? These companies are not really trying to do that, right? But they had record profits. So the AI thing just got really kind of justified and got supported as being a real thing, right? Because everybody was worried about there being an AI bubble, just like there was a dot-com bubble back in the day, right? Real estate bubble, right? Everybody's afraid that this thing's gonna pop and it's not gonna deliver on what it says it's gonna deliver or can deliver, right? So, so we're looking at the covariance, all right? Let A and B be constants, all right? So we'll go look at that. And then use these results to derive the expected return and variance for a portfolio. All right, so we're looking at portfolio management. What's the thing?
It's the same thing with crypto though.
Same thing, yeah, exactly.
But
Yeah, I'm saying.
it's not real, like,
What's that?
I mean, talking about like expected return and stuff on crypto is,
Yes, real. Why wouldn't that be real?
it's like, you know, those small coins.
Yeah,
They buy and sell and buy, so you buy thousands of them.
Yeah, yeah,
to
yeah.
make a dollar and
Yeah.
stuff like that. Will that like still have the same thing, expected return variance and all this?
yeah. They say the same thing. It's just that, again, you'd have to go back and look at the coin itself, right? What is the inherent value of the coin, right? Dogecoin, Shiba Inu, or
Ethereum.
Ethereum, right? Or XRP or Bitcoin, right? So Bitcoin, what is the value in Bitcoin?
It's about 100,000 right now.
No, I'm saying what is the value? Why is Bitcoin $100,000? Why well it's not it's $90,000, right? But why is it so much?
Limited, it's like controlled.
Okay, scarcity is part of it, right? But why is Bitcoin
Cause digital currency.
digital currency, right? It was the first one. It was the first digital asset out there, right? But how are people using it is the question, right? What is the utility, right? There's got to be at least 100,000 coins out there right now. If you want to make a coin, you can make a coin right now. You can make a coin right now and put it on the market and sell it. Okay? The thing is, what does your coin do? What is the utility in your coin? If your coin has no utility, it's called a meme coin. Okay? And so meme coins, again, when you go back to the art and go back to the NFTs, the value is inherent to the people that are using it, that think it's important or think that it's valuable, right? That's why most of the coins are trash. 95% of the coins out there are garbage. I won't waste my time. I'm telling you the truth. Ethereum's all right. XRP's all right. Litecoin's okay. You know, don't buy Doge. Don't mess with that,
Oh, yeah.
right?
Politics.
It's just you gotta look at the utility of this stuff, right? So it's all real. And Bitcoin is good because first it's popular. I'm gonna say it's good because Bitcoin eventually is gonna fizzle out, right? It's basically a store of value, right? Same reason why gold is valuable, right? But gold has utility
Anywhere, everywhere.
everywhere, right? Gold has been around for
Millions.
the beginning of time, right? And it's important to people, but it's also important to people because it does certain things, right? The way it conducts electricity, the way it's malleable, right? I can kind of take it and bend it and put it in different shapes and do whatever I need to do with it, right? Copper, gold, silver, platinum, cadmium, right? Nickel, right? Tungsten, titanium, right? All these particular materials are all in your computer. Without those particular materials, those minerals and those things, we wouldn't have the computer because we couldn't make microchips, we couldn't make transistors. All right. So this is why it's important that you understand the landscape when it comes to why we are kind of treading lightly with Russia, why we're treading lightly with Ukraine, why we're treading lightly with China, right? Lithium, right? Because they have these stuff in abundance. Africa, right? Diamonds, right? Are in Africa.
All of
Okay. Africa has so many things, it's ridiculous. Right? All right. So let A and B be constants. Expected value of AX plus BY equals the A times the expected value of X, B times the expected value of Y. So basically, we're looking at weights, is what we're really looking at, right? Okay. And we're going to get into it here. All right. So let R be the random variable for the return of the portfolio with assets A and B. All right. So the R is the rate of return, right? Or the return for the portfolio. We have two assets in there, asset A and asset B make up the portfolio. Okay. B random variables for the return of asset A with weights A and weights B, where weight A, weight B equal to 1. Okay. All right. Expected return of portfolio is how, this is the formula for it, right? Expected return, expected value, whatever, the mean, at the end of the day, is equal to the weight of A times the expected value of the return of A, of asset A. Okay, so this is all asset A, this is all asset B. Okay, so remember when we were talking about weights and we talking about grades, right? And A equals a 4, B equals a 3, C equals a 2, D equals a 1, right? That's how you get the GPA. Okay, it's the same thing here. Those are weights. So we're going to use a weight here, okay, to figure out, okay, based on the assets in the portfolio, which one carries the heavier weight, right? This is the same thing with NVIDIA. NVIDIA is within the NASDAQ, right? The NASDAQ has 100 companies in it, right? And every time it kind of rotates depending on market cap and all this other stuff, right? So NVIDIA has a huge weight in the NASDAQ because it's one of the bigger companies, right? And so if NVIDIA is not doing well one day, right, it can drag the market down because it's heavy within the 100 companies. It holds the most weight, it has the most capital, sort of, right? Make it easy, right? So if NVIDIA is going up, then it means more likely the NASDAQ as an index itself is going up, right? It's taking everything with it, right? Rising tides raise all ships, right? Everybody heard that term before? Rising tide raise all ships, right? That means that, hey, when the water comes up, we all gonna eat, okay? This is gonna benefit everyone, okay? So if NVIDIA is heavy, or we got this company or this one of the assets that are heavier than the other asset, if it doesn't do well, it's gonna bring down the value of the whole portfolio, right? But we need to know that, right? So we can calculate the probabilities, but we need to know what the weight is. Standard deviation of the rate is a positive square root of variance. We already know that. Okay. The risk of the portfolio depends on the risk of the assets, but the interplay between them. Okay. For example, one asset does poorly, the second may serve as an offsetting factor. The correlation is easier to interpret, right? It's kind of like hedging your bet, right? You go and you say, all right, I'm gonna buy this, right? But I know, it probably not gonna last long, so I'm gonna buy another one as a backup, sort of, right?
How does the US dollar work then?
As far as what?
As far as the correlation, what does it have correlation?
The US dollar is.
No gold, because in '60s they finished the thing, right? The gold.
Yeah, we don't use, it's called a Brentwood system.
Yeah.
We got rid of that a long time ago, right? So basically we just print money.
Yeah.
That's all we do, we just print money, okay? But the problem with printing money is that you're in a situation like we're in now. High inflation, can't bring it back down, right? Because anytime the government needs money, just print some more. Put it in circulation, right? But after a certain point, the money becomes worthless. Right? It's just paper now.
It's terrible.
Because there's just so much of it. You know, so that's why you see some of these economies dying because they just print money, right? And so this is where inflation comes in. And also the dollar is the reserve currency of the world. Right? And so you can go anywhere in the world and use a dollar to buy anything for the most part. Right? Now, they're getting away from that, right? Because everybody, the United States is pissing everybody off. And so everybody's kind of like, you know what, with this new technology, we don't need the reserve dollar. We don't need the dollar to be the reserve currency. We don't have to use it, right? Because if you know, how's oil bought? Anybody know how oil is bought?
US dollars.
It's US dollars. Okay? If you want to buy oil, like China, they have to take the yuan, go to the bank, hey bank, I need 10 trillion US dollars for my yuan. Then they take the 10 trillion, they go to OPEC, wherever they get their oil from. Here's 10 trillion US dollars, give me my oil, and they go. Right? What's the problem with that?
Yeah, the converting.
The conversion rate.
Yeah, it's bad.
Right? The conversion rate is terrible. Okay? The countries lose out, right? So now what's happening is that a lot of these countries are getting together and saying, look, we don't need the dollar anymore.
Bricks.
There you go. right? Let's just use our own currency and we just convert it into your currency. Sounds good to me, right? They just did it 2 weeks ago. China just bought oil from Saudi Arabia in yuan, right? Guess what? United States panicking, right? Because we lose reserve currency status, that's a big deal. You don't have as much leverage, because that's what really controls the financial markets.
This Saudi prince was there yesterday, cause.
Yeah. South Bin Laden, whatever his name is. All right, so let's look at this, right? Okay, so this is the variance, this is the expected return on the mean, right? This is the variance, right? The weighted average, the weighted times variance, plus the weighted weight for the second asset or Bravo asset times the standing deviation or the variance, excuse me, and then added to the two weight of A, weight of B. This is what you call rho. Okay, it's funny P, it's called a rho. Okay, that's the covariance. That is the correlation. Okay, this is the correlation of a population. Right, when you see that, it means the correlation of population. When you see this is the correlation of a sample. Sample correlation. Okay, when you see that, or something like that, population correlation. Okay, correlation always falls between -1 to 1. Okay, and the negative only denotes direction, doesn't denote value. So it just tells you, is it below the 0 or is it above the 0? Okay, -1 to 1. Okay. So either way, so we're looking at the covariance and they're using the correlation as the covariance, right? To figure out, okay, how these two work together. Okay. All right. So we got stock A, stock B. We got the expected rate of return, which is the mean, 9.5%, right? For stock A. Here we have 7.6% return, right? For stock B. Our standard deviation for asset A or stock A is 12.93, 8.20 for B. And then we have the correlation here. It's 18.60. Okay, so calculate the expected return of the portfolio. Okay, well, how do we do that? Let's go back here. There's the formula right here, expected return of the portfolio. Okay, so let's work through that. You guys can work through it at your desk if you want, kind of figure it out, or if you want to come up here, demonstrate your fantastic skills. That's always an option. All comers, anybody? Once, twice, 3, 4, 5, 6, 7, 8, 9, 10 times. Anybody want to try? Nothing.
Maybe see them, for example.
Too new, too new. Too new, too fresh. All right, okay. So let's look at this formula here. So expected return, let's write this formula down. All right, expected return equals weight of A, E, R A, excuse me. Plus weight of B, E, R, B. Okay, so this is the formula for my expected return or my mean. Okay, so go back to our, dang, I left my little clip over here. Let's go back to our numbers here. All right, so if we go down and we look at the little formula, return, okay, so let's look at the formula, right? Weight of A, of asset A. What's the weight of asset A? Do we have it? We don't have the weight of asset A, right? What is the weight of asset A? What are the weights?
The value?
No. When you say volume, what do you mean by volume?
No, the value.
Okay, yeah, okay, the value. What is it? Tell me.
I thought they didn't tell us.
No, it's equal to 1.
Oh, yeah.
It's equal to 1,
Yeah.
but
It could be less than 1.
1 to,
Okay, so-
negative 1 to 1.
So think about it this way, right? What they're asking what the weight is, right, of the portfolio. Right? So we know that in portfolio, stock A is 40,000, stock B is 60,000.
Mm,
What is the total amount of the portfolio?
100,000.
100,000, right? So what is the weight of asset A? What is the weight of asset B?
Combined together, that's 100,000. So 40 and 60?
100,000, right? 40,000, 60,000. Okay? But what is the weight?
You have to square root it.
No.
1.
No. What is the weight? How much of this is a percentage of that?
0.4, 0.6.
0.4 and 0.6.
Oh, you have to.
0.4, 0.6. Okay? 0.4 or 40% of this portfolio is asset A.
Mhm.
60% or 60,000, right, is asset B. That makes the 100,000, which is equal to the 1. Right? The whole. Right? Always think the 1 is a whole.
Like
Right.
the other problem we did.
Yeah, it's always the same in math.
Okay.
1 is always the whole. It's not just, hey, it's a 1. It represents the whole because it could be any number. Like right now, our whole is 100,000 is equal to 1. That's our 1, right? The 1 is a theoretical 1, right? Just saying that, hey, it's the whole thing, right?
Mhm.
So we have WA at 0.4 and WB as 0.6, right? And how did we get that? What we did was take 40,000 divided by 100,000, right? And then 60,000 divided by 100,000. And it gives you the weight of each, okay? Because our total portfolio is worth 100,000, so we got that, all right? So we're good, okay? So we got, write this down. We got weight of A equals 0.4, weight of B equals 0.6, right? Everybody remember how we got that, right? So let's plug and play here. So 0.4, okay? Multiplied by the expected rate of return for asset A, right? What's the expected rate of return for asset A? All right,
9.5.
9.5. All right. Put more oil here now, okay? 9.5 plus weight B,
0.6
0.6,
multiplied by 7.6.
7.6. All right. All right. So what we got here?
It's 3.8 plus 4.56.
That gives me what?
Gives you 8.36.
Okay. 8 point.
Wait, we're multiplying 0.4 times 9.5.
Uh-huh. Yep. Because we're multiplying the weight times the expected return of asset A, which we have up there. They gave us that, right?
No, I just got something else at first. That's what I was like,
What'd you get?
no, I did it wrong.
Okay.
I got the right thing.
Okay, all right, so 8.36, right, is our expected return, right? So 8.36 is what is the average return for this portfolio, right? And we would expect to get, okay? So we calculated that. Let's see if we're right. We're right, 8.36, all right, okay. Calculate the correlation, all right. Let's see what they got. Did they give us the formula for correlation? No, they didn't, right? Because it's super long.
That's right.
Okay, so we're gonna just go with what they gave us here. Okay? Covariance RAB equals standard deviation of AB equals 18.60, right? So now let's calculate the correlation. All right, so I'm just gonna go straight to it because they don't give us the formula and it actually is very long process.
Use calculator to do the correlate.
You will use Excel or some other software.
Yeah.
Yeah, to do this, a statistical calculator. All right, so basically, we're taking the 12.93, which is the standard deviation here, right, which they gave us, times the standard deviation of asset B, and that gives us 0.1754, right? So we got 0.1754 as our correlation, okay? So our R equals 0.1754, whatever it is, right? Okay, now is this a strong correlation or a weak correlation?
Week,
Weak, why?
0.174%,
Okay, and
as compared to 8.36, right?
no, 8.36 is the rate of return.
All right.
So that has nothing to do with it, right? It's the rate of return. All right. This number here represents the relationship between the two assets, between the two rates of return. Okay. So basically, they have a weak relationship because correlation goes from -1 to 1. Right? The closer you are to 1, the more the stronger the correlation, right? So this is the normal guy. 0 to 0.3 is weak.
And that's closer to 2, right?
What do you mean?
The answer that we got, the 0.17.
No, it's just no,
Well, it's, I don't know what it's close to actually.
yeah, it's close to the 0.18. It's close to 18, right? But it wouldn't really matter, right? We wouldn't necessarily round this up or anything like that. We just look at it and go, okay, 0.17. Where does it fall on the spectrum between -1 and 1, right? So I'm telling you now, so let's just say we dropped it to 2 decimal places, right? 0.17. Okay, make it easier. Weak is 0 to 0.3. Moderate is 0.4 to 0.6. 0.7 to 1 is strong. Okay? All right. So, because it's such a weak correlation, we really can't rely on their relationship to determine whether or not they have an impact on each other, right? Just because one does something doesn't mean it's gonna do something, the other one's gonna do something else, right? So we go, okay, fine, that's the correlation, that's the way it is, right? So we use that though to calculate, once we get the. Well, it can't be that, it's fine. What just happened? Technology. Okay, so we have the correlation, right? 0.1754 returns have a weak positive relationship, right? And then now we just use the variance. We use the variance formula, right? We go back here. Okay, what's the variance? The weight times standard deviation plus the weight of B times the variance, excuse me. And then you go through the formula, right? So as you can see, it's basically understanding the formulas and know what's going on, okay? And again, a lot of the times you're gonna get this. You're gonna get like all this data, right? You just gotta make sure you put it, assign it to the right variable, put it in the right place, because it's really plug and play after that, all right? All right, so calculate the variance standard deviation in the portfolio, kind of did that already, boom. We followed the formula, and then we're gonna take the square root of 59.89, that gives 77.4%, right? Again, the standard deviation helps to create a range, right? So if the average, right, is 8.36, and I tell my client, like, hey, you'll be within one standard deviation of the mean, right? Next question would be, well, what's the standard deviation? It's 7.74. So you can get anywhere from a 1 point something% return to a 15 point something return or 16 point something return. Okay? That's the range for the first standard deviation, right? And you'll find standard deviation, it is very helpful in understanding, okay, where do I assume things fall, right? So for context, you guys have had Chips Ahoy before, right? Oh, back in the day, the Chips Ahoy, been around for a while. Nabisco company, right? Chips Ahoy got sued because the lady got the package, she took out one cookie, it had 5 chips in it. She took out another cookie, had 1 chip in it. She took out another cookie, had 2 chips in it. What's the problem here?
Not enough chips.
Not a chip, but what's really the problem?
Inconsistency.
Inconsistency, right? Inconsistency. The standard deviation helps you be consistent, right? So what they did was they went back in and looked at, okay, if I have a cookie of this circumference and this surface area, how many chips can I feasibly put in this thing and not make it look crazy, still make it taste good, and not be overpowered by chocolate chip? People still get the cookie, or it's whatever scientific genius they did, right? Once they figured out that number, right? That's what they did. They calibrate the machine to say, okay, every cookie gets 6 chips. Okay? But guess what? We have to have a buffer. Because maybe the cookie dough gets stuck or something happens and the machine spits out extra chips or doesn't spit out enough chips, whatever the case may be, right? You have to have a buffer. So this is where the standard deviation comes in, right? So Chips Ahoy got sued. They went back and said, look, every cookie is gonna have 6 chips, plus or minus 2. So if you get a cookie and it's on average, it has 6 chips, but if it has 4 chips, or if it has 8 chips, we're good. You can't sue us because we're within one standard deviation of the mean. Okay? We said we promised you 6, you only got 4, or you got 8, right? So we're cool, right? Anything past that, then you're gonna have a case to take to the court. Like, hey, my cookie had 1 chip in it. That's outside of my 2 standard deviations, right? So then it's like, okay, what happened? Right? This is where you shut the production line down and say, okay, what's going on? Oh, machine number 2 isn't spitting out right. It needs to be recalibrated. Oh, it broke. Or hey, Jimmy tripped and he put too many cookies in there and too many chips in the thing and it spit out all these chips. Or he didn't put enough chips. We got a new guy. He didn't put, he's supposed to put 10 chips in there. And these are real issues. Okay? So that's kind of what standard deviation helps you do. I don't know why this computer keeps shutting off though. So weird. Okay. All right, so we're done with that, okay? Now we're gonna get to the binomial distribution, the fun stuff, all right? So the Bernoulli process, right? Bernoulli was an Italian mathematician. He came up with all this good, cool stuff, all right? So there are 3 different types of probability distribution when it comes to discrete. There's the binomial, there's the Poisson, and then the hypergeometric, okay? Most times we'll just focus on the binomial and the Poisson. Okay, those are the 2 that really we mess with, okay? The Bernoulli process is the overarching concept, right? And all it's saying is that, hey, there is an independent number of series of activities, right? And in identical trials and experiments such that on each trial, there's only 2 possible outcomes, right? When it comes to binomial. There's success, well, it comes to Bernoulli in general. Success and failure. The probability of success and failure remain same from trial to trial, right? And we use the P to denote the probability of success, right? All right. So basically what it's saying is like, look, when you only have 2 outcomes, right? How do you determine the probability? All right. There's only one or the other. You're either gonna win or you're gonna lose. You're either gonna pass or you're gonna fail, right? What's the likelihood of me passing? What's the likelihood of me failing? All right. So that's the binomial, right? But in general, it's called Bernoulli, the Bernoulli process. Okay. All right. The binomial itself is to find the number of successes achieved in the n trials of the binomial process. The possible values are 0, 1, k, and n. All right. Don't worry about the k right now. We'll get to that. Maybe. All right. So these are all the possible values for when we talk about binomial, right? Think 0, 1, right? What does that remind you of?
Computer.
Computer, right? Bytes, right? When we talk about 0, 1s, right? 0, 1s, when coding, right? It's either on or it's off, right? 0 is off, 1 is on, depending on how you code it, right? So the probabilities associated with the possible value, right? So some examples, customer defaults and not default alone, customer react positively or negatively to social media campaign, a drug is effective or ineffective, right? So all these are real life scenarios that all of us go through. When you go to the bank to get a loan, they do a risk assessment, right? How likely is this person to pay me back, right? What is the criteria that they use to make an assessment? Your credit report. Okay, that's what they use. All right. Okay, so here's an example of binomial distribution, all right? So what we're looking at is we're looking at all the possible outcomes of this particular situation, right? 85% of customers will use a credit card, right? I have 3 customers, right? And I want to know what are the chances that they use or don't use their credit card, right? So basically, the way you read this is you have to follow every path, right? Anybody ever done path analysis? Okay. You have to follow every path, right? So the first one is SSS. That's a possible outcome, right? All 3 customers can use their credit card. S means use, F means fail, right? Success, use the credit card, failure, didn't use it, right? So the first event is okay, all 3 use the credit card. Okay. The next one is okay, 1, 2, F. So the first one used it, the second one used it, but the third one did not. That's an outcome, right? The next outcome could be SSF, but we already have that, right? So guess what? We're gonna go SFS, right? That's my next possible outcome. And then we have SFF here, okay? So you have to kind of follow the path and make sure you account for every possible outcome based on what you have as far as success or failure, right? That's why it's easy to predict the probability because there's only a certain amount of outcomes possible, right? And so because of that, I can determine pretty much what all the events are going to be, what are all the possible outcomes going to be, right? Same thing here, right? We go FSS, that's the first one, FSF, second one, FFS, and we have FF and F, okay? And as you can see, it tells you 85% of customers will use a credit card, right? So based on the scenario on the event, SSS, if 85% will use a credit card, we have 0.85, 0.85, 0.85. The chances of all 3 of them using a credit card is 0.61, okay? So it's just an example to show you. This is not anything crazy here, right? And you can tell here, 0 chance, right? Here is 0.034. One person using it is 0.0573, which we have to pretty much add up a couple of these together, right? 2 of them using it, 0.352, 352, and then 3, 6.41, right? So we would basically add up each of the events based on the probability that, okay, 2 used it, 3 used it, whatever it is, right? Based on right here, right? All 3 used it, 0.85. 2 used it, but 1 didn't, 0.885, 0.5, 0.10. So you would add it up to get a cumulative distribution, right? So you can figure out, okay, like, what does each one mean, right? If all 3 used it, okay, right, over here, what's the chance of all 3 using them? 0.6141, right? Because you calculated here, 0.85, 0.85, 0.85, okay? Based off of what they set up there. All right, so this is the formula for the binomial distribution, right? Probability of x equals nx, right? N being the number of events, okay? Possible events, the population, right? X being the actual number of success or failures that you're looking for, right? Probability to the x, okay? Multiply 1 minus p to the n minus x, right? Equals this, all right? And this is what you need to focus on right here. This is the formula that you need to lock in there, right? N factorial divided by x factorial multiplied by n minus x factorial times the probability to the x power multiplied by 1 minus p to the n minus x power. Clear as mud, right? Easy, right? All right, nothing complicated here. You got no exponents, right? And how to use them on your calculator, right? Everybody familiar with exponents and how to use it on a calculator? You know, I showed you last week, right? There's one other that you have to get familiar with, and that's E, right? Everybody know what E is? Bless you.
Thank you.
What is E?
Exponential.
No. What's E? E equals MC squared. What's E? Energy? No. E equals MC squared. And it's kind of energy, but E equals MC squared.
That's a linear formula, right? So E equals energy equals.
You guys should know this. E equals MC squared. Albert Einstein.
Yeah.
What is it?
Oh, 3.14?
No, that's
Oh, we
it.
took
That's
a pi.
that's five. That's five. That's something different. That's something different. E equals MC squared. E is the speed of light. 2.78 times 10 to the something power, right? The speed of light.
Energy, right?
Energy.
Yeah.
Yeah, energy. And then, right? Mass times constant rate of speed is something like some nonsense like that, right? I'm not smart about that, right? I just know what E is, right? There's a button on your phone. It's a little E with an X as a superscript, right? You need to learn how to use that.
Yeah.
Okay? Because that's going to be part of the formula. All right. So basically, if you're doing a binomial, you're looking for this. All right. This is for x equals 0, 1, 2, k, and n. All right. Again, this is the domain, right? Because you can either have failure, success, can't have both, right? You can have k, right? But you have a limited amount of outcomes. But this 2 here is the number of outcomes possible, right? So, and then by definition, 0 factorial is equal to 1. All right. All right. Let's go to a little example. All right. The mean is expected value of x equals mu equals n times p. Number of events in the population times the probability, okay, of that event. The variance, same thing, n times p multiplied by 1 minus p, okay? All right, so in the United States, about 30% of adults have 4-year college degrees. Suppose 5 adults are randomly selected. What is the probability that none of the adults have a college degree? All right, so.
Nice simple probability.
Huh?
A simple probability.
Simple probability, what do you think it is?
30%.
30%. All right.
So that's 0.3.
You see, he's going with 30%. Anybody got a different answer?
No. I'm still going.
Anybody got a different conclusion here?
1.5 people don't have a degree.
1.5 people?
Yeah.
How'd you get 1.5 people?
0.3 multiplied by 5.
Ah, 0.3 multiplied by 5. Huh. Let's see. Did we follow the formula? That what you used?
No, I.
Okay, all right, let's checking. Okay,
The formulas just look like the.
it is a lot. It's a lot, but it's not. Okay, it's a lot, just a bunch of exponents, all right? So, what is probably none of the adults have a college degree, right? So what we're really asking is, what is the probability? Using it. What is the probability here of x equal to 0? That's what it's asking us, right? What is the probability that none of the adults have a college degree? All right, so go back to our testy formula, right? Our formula is, what is the formula? n factorial divided by x factorial n minus x factorial to the px minus multiplied by 1 minus p to the n minus x factorial, is that right? Yep, that's cool, okay. All right, so. Both down here, right? So first thing I would do is figure out, okay, all the variables. What's my n? What's my x? What's my p? Okay. All right, because those are all the variables I have, n, x, and p. Straight up, okay? All right. What's the probability none adults have a cause degree? All right. So if I go here, right, what is my n?
30.
30.
Or 0.3. Or 5.
5.
5.
5, right? Okay. 5 my n. Okay. Okay. Oh. Da. All right, what's my x? Okay, yeah, all right, just making sure. My x is 0, that's right. Crazy. I already have my x. What's my probability?
30%.
30%. Okay. All right, so now we're gonna do is just go in here, right, into the formula. All right, so n factorial is what?
5.
5 factorial divided by 0 factorial multiplied by 5 minus 0 factorial. All that to the p, which is the 0.3 to the 0 power. Okay. Anybody good so far? Okay. Multiplied by 1 minus p, which is 0.3 times, oh, to the n minus x power, to the n 5 minus 0 power.
So it's p to the 1 minus, what is, p to the n minus x.
Y'all just looked at me like, what are you talking about?
Yeah.
Oh, okay. 5 factorial, right? Because we have all our variables listed here. Okay, n is 5, x is 0, p is 0.3, right? Probability, the data point we're looking at, and the possible, or what, and then what we want, right? 5. All right, or what we have going on anyway, that we picked out. So, okay, make sure I put this down right. All right, you get this and that. Times p to the x, okay. Yep. The whole thing, that's that part. All right, got it. All right. Now, what's 5 factorial? Oh, actually, let's go through this again. All right, so my n, right? I got my x. I got my n again. My x, 0. I got my p to the x power, 0, right? Multiplied by 1 minus my p to the n 5 minus x 0. Okay? Easy plug and play, all right? All right, so now, what is 5 factorial?
Isn't it like 5 then 4?
4 times 3 times 2 times 1. So what is that?
5 times 4 times 3.
Look on your calculator, you see the exclamation, you see the exclamation point, you see X and then you see the exclamation point next to it. That's factorial.
So put the 0 exclamation times 5.
No, just put Just
Just
put
put 5 and then put the,
exclamation point,
120.
120. So 120, okay, divided by 0 factorial is what?
1,
1, okay. 5 factorial, because 5 minus 0 is 5, so 5 factorial is what?
120.
120 again, right? Multiply by 3 factorial, which is
6.
3 factorial, 3 factorial 0 is 6.
No, 0.
It's,
Oh.
is it 0?
Everything's a power of 0.
3 factorial, then 0? What do you mean?
So 3 to the, not factorial, to this power, excuse me,
Oh,
Anything to the power of 0 is 0.
is 0, right?
Yeah.
Okay. We sure about that?
Yeah.
3 to the power 0, 0?
0. Anything power of 0 is 0.
Okay. Alright, I'll roll with that. Okay, so 1 minus 3. 1 minus 0.3 is what? 0.7?
Oh, 3 to the power of 0 equals 1.
It's equal to 1, right?
Wow.
Thank you, Bianca.
No, I mean, it got me to.
No, I knew what the answer was. I was waiting. He was so confident in himself. Like 0, 0. 0's got to be 0.
We're trying to go home.
So 0.7, right? 1 minus 0.3 is 0.7 to the 5th power, okay? So what we want to do here is, okay, 120 divided by 120 is 1 times 0.7 to the 5th power is what? What's 0.7 to the 5th power? Anybody?
I don't know how to do the raise to whatever number you want on my first.
Just look for the E, not, look for the, yeah, look for the exponent, let me see. Oh, it's because you ain't got it. Do it like this.
And then
So then,
0.7.
right, and then you wanna do, what's the exponent thing?
Right here, second.
No, not. Exponent. Sorry. Oh, you got an E button, okay, cool. No, it's still not working there.
Maybe I don't have it.
0.7. There you got it. Ah, 0.7. E5. There you go. Okay,
So what do you wanna do? You
Yeah,
just put E.
so you put the point. You put the 0.7
Mhm.
and you press the E. And then you put the number you want it to go to, 5, and you press equal.
Okay.
Yeah, we're capturing. 0.7 E. Uh, 5,
So, okay,
10.06. Everybody got that? It's 10.68, something like that. Okay? That does not seem right. That's not right. That's not right.
0.7 to the power of 5 is 10.6.
And the long calculator. Yeah, okay, yeah, 0.30, 0.70. Yeah, as I said, that don't sound right.
I don't know if my calculator has it.
They all have it.
It's 0.16.
Yeah,
807.
okay.
Yeah, 0.1680807, which is 81.
Oh, you press the X with the Y exponent, and then you press whatever number you want.
Okay, that's how you.
There it is, yeah. I
is.
was like, wait a minute, something ain't right. Led you astray. There's a whole statistical calculator for this. And you can tell I don't do this.
Yeah.
And we are. All right, that's better. 0.168, right? Why did I know was wrong? Why did I know was wrong?
Because it has to be a number closer to one.
It has to equal to one, period. It can't be more than one.
Mhm.
If it's more than one, something's wrong, all right? All right, so we have that. That's one times that. Okay, so 0.1687 is our probability. Okay. 1687, 1681, same thing, close enough. All right. Okay, so what time is it?
742.
Okay. Let me just run through this real quick. All right, so the next question is, what is the probability that no more than 2 of the adults have a college degree, all right? Same question, but you just gotta look at it and go, what it's asking for, no more than 2, okay? So that means you basically have to say, okay, less 2 equal than or less than 2, okay? So what you're gonna do is, same formula, you're just gonna have to add up the different probabilities, right? Because now it's saying 2 or less than 2. So that's inclusive of 0, 1, and 2. Okay? So if the probability of,
Oh, okay.
You see what I'm saying?
Probability of 0 was 0.168, so now we
Right.
gotta do 1 and 2, and that's it.
right,
And-
so basically you'd have to go in and say, what's the probability of 0, what's the probability x equals 1, what's the probability x equals 2, right? All you're doing is the same formula, you're just plugging it. Now, instead of x equals 0, it'd be x equals 1, x equals 2. So you have to figure out each independent probability, then add it up to what you need, right? I don't think it
It's
gives
a
us,
long.
it's a long process, yes. This is why we use calculators, right? But we're learning here, okay? We're learning
But you
here.
still have to write it down, right?
What you mean?
Write down the problem, write it to figure it out.
Yeah. I mean, you don't have to. You can just put in the inputs. It'll ask you for n, x, and p, and it'll calculate it.
What? Which calculator is that?
Excel will do it. Statistical calculator will do it, and you can put it in ChatGPT, it'll do it. You do a number of ways, right? So, okay. Same thing here, variance, attenuation. Okay, these are the what you would call it, distributions as far as Excel, the functions go. Okay. So if you go to the drop down on Excel, you'll see where it has, statistical calculator, whatever. Go in there and it'll have all these different things. Don't worry about the R. You guys are not gonna use R unless you guys are planning on doing some AI or engineering stuff. Okay? Here is all you see how it says, see what it looks like for? XNP0, XNP. It has a 0 here for failure, 1 for success, right? So it's gonna calculate both. So then it give you the proper probability, but you see what it's asking for, same thing we had here. Okay?
We only halfway through this.
Huh?
We only halfway through this course.
No, we're done here. We're almost, this is this.
Talking about like being on week 4.
Oh yeah. This the halfway paint. Yeah.
I'm done.
It's a lot. This class is a lot to stuff into 8 weeks. Typically, I like to do it over a semester because a lot of stuff. But sorry. Okay. So now, same thing, except now we're going to use the Poisson distribution. And the only difference between this one and the binomial distribution is that this gives you an opportunity to figure out in a certain amount of time interval or space, right? So let's just say, how many people do I expect to come to a grand opening? All right, what's the chance of somebody coming to grand opening if it's raining? Right, in this between 6 and 9, right? That's how restaurants again figure out when's the busiest time of the day, right? Dinner time is the busiest time, or lunchtime is the busiest time, right? Because they figured this out. Or they have somebody else do it for them. All right. Number of successes counted in overlapping, not overlapping intervals are independent. Probability of success in any interval is the same for all intervals equal size and is proportional to the size of the interval. Okay. At the end of the day, Poisson random variable is the number of successes achieved in a specific time or space interval. Okay, so this is specifically looking at time, taking that into consideration, or space. Right? When we mean space, we don't mean like space. We mean like space, like ether sort of space. All right. All right. So this is the formula for the Poisson. Okay. For Poisson random variable x, the probability of x successes over an interval of time and space is probability of x equals x is e to the negative mu multiplied by mu to the x divided by x factorial. Anybody get that? Good?
Yeah, it's amazing.
Okay.
Oh my goodness.
Mu is the mean number of successes. E, 2.718 is the base of the natural logarithm. Okay. Basically, we talking about base 10, base 2, right? Base 8, that kind of thing, right? Depending on what we're doing it for, what we're using it for, right? The mean is the expected value of x, which is the mean, right? The variance is variance x is equal to variance equal to e of x, which is equal to mu. So basically, the mean and the variance are pretty much the same for a Poisson. Okay. All right. Our example here, right? Back to the Starbucks. Anne is concerned about staffing needs at the Starbucks. She manages to believe that the typical Starbucks customer averages about 18 visits to the store over a 30-day month. A, how many visits she'd expect in a 5-day period? What's the probability that customer visits the chain 5 times in a day? In a 5-day period, what's the probability that customer visits the chain no more than 2 times in a day? In a 5-day period, what's the probability that customer visits at least 3 times in the 5-day period? All right, I'm going to skip all the semantics here and go straight to it. Given the rate of 18 visits over 30-month, the mean for 30-day period as the mean 30-day is equal to 18. So the mean for the 5-day period is 3. Okay? How I get that? Anybody see how I got that? If for 30 days, this is annoying. Let me start doing this. No, we're definitely not doing the hydrogenic. Okay. Okay, I'm sorry. All right. How do I get the 3? Okay, so for sake of time, right? 30-day period, 18 visits, right? I'm looking at 5-day period. How many 5-day periods are in a 30-day period?
6.
6, right? So I need to divide the average visits
Oh.
by the 6. And that'll give me the average visits for a 5-day period. That's all. Okay? That's 3. Simple, right? Okay. The probability of x equals 5, right? Because we're looking for 5-day period, right? Is e to the negative 3, right? Which is the mean, right? Multiplied by 3 to the 5th, right? Which is the x, right? E, once you put into the calculator, right? So, and then divided by 5 factorial. So go ahead and try this.
The E is basically 10, right? Logarithm.
No, E is 2.78.
It's not log.
It is log. It is log. But it depends on, that's the constant.
Okay.
So that doesn't change any. Yeah, E's a constant. But it's a logarithm. But you could have, base 2, base 8, base 10, base whatever. Anybody any luck? Figure this out yet? Let's see. E to the negative 3. E. What we got? What we get? What we get? Hmm?
Doing the B,
Yeah, we're doing B.
isn't it 0.100?
No, it is, but is that what you guys got?
Yeah, cause 5 factorial is 120. And what is E?
2.7.
2.78. E's a constant. It's the speed of light.
Yeah, okay, so 2.78.
So
I
Always
can't
be
see.
2.7.
you
Is
can't
that
see.
to the
Oh,
next
it's so tiny. Yeah, yeah. So let's go back to the original formula here. So you can have an idea, right? This is our Poisson formula here. Okay. So let's just go e to the negative mu, right? No, yeah, times mu to the x divided by x factorial. This gives us the Poisson, right? Yeah, funny name.
French.
It is French.
Wait, can we go back to the other thing,
Which one?
the other slide? The mu was,
Oh, you wanna see this one?
so it's 3 to the 5.
Yeah, so we'll stay here. All right, so let's do this the easy way. All right, what's the E?
2.78.
Okay, what's the R mean?
-3.
No, let's do it variable by variable, right? So
3.
what's our mu? 3? All right, what's our X?
1,
What's our X? We're looking for a 5-day period, right? X equals 5. Okay, yeah. All right, so X is 5. All right, so let's just plug and play, right? So 2.78, all right,
to the -3.
to the -3, multiplied by 3 to the x, which is 5, all right, divided by 5 factorial. Okay, all right, so what is 2.78 to the -3? And what is 3 to the 5th power?
11.31.
Which one?
3 to the 5th power.
11.31. What is 2.78 to the -3rd power? What is e to the -3?
0.047.
6. Yeah, 465. 57.
0.0465,
5.
7, okay, close enough. Alright. Divided by 5 factorial, which is 120, right?
Mhm.
Alright, let's move this down. 0.465 times 11.31 is what?
It's 0.5264
Okay,
divided by
Let's go.
120 is 0.00437.
say that again,
0.00437.
0.004.
That's a different answer than what the thing says.
Let's see. What do you got? They got 0.10, we got 0.0047. Okay, where we did mess up at? Scratch that. All good. Alright, I'm sure it's the E.
E is just 2.78.
And 2.7 times 10 to the something negative, something, but I don't know what that number is. Normally, the thing has it. So, let's see. E to the 3 negative.
It is 0.0498.
You got what?
0.0498.
Zero 4 point.
0.0498. Isn't that it?
No, that's the probability of X.
I use E to the -3.
I
Yeah.
got 0.0465.
Isn't that right? This right, Professor?
0.497.
E to the -3.
Yeah, let's see. Yeah, that's what you gave before, right?
Yeah, it's
Yeah,
just
it's
like.
like. All right.
Is 2.71828. That's what E is.
Right, but we need it to the -3, right?
Yeah, but I was doing 2.78, and that's probably what threw it off, because it's 2 point,
Oh, no,
Seven.
you typed it in manually?
yeah.
Oh, don't do that. You can use the E. Yeah, use the E.
I don't have the E on me, like.
What?
Oh, like the lowercase E?
Yeah, little E.
Mhm.
Yeah, that's why I keep getting 0.0498.
Okay. Okay, so if you press the E, and you press equal, it give you 2.718, right?
Mhm.
And you take that to the -3 power, so use your exponent. Point 04978, that's what you got?
Mhm.
Okay,
Oh, I got it now, 0.04978.
okay, so leave it at that. 3 to the 5th is what?
11.31.
243?
243?
Let's see if I'm right. Yeah, 3 to the 5th is 243. Think about it. 3 times 3 times 3 times 3 times 3, 5 times. 3 times 3 is 9, 9 times 2 is 27, 27 times 3 is 50 something.
Yeah,
and
no,
times
I
that.
got it right there.
Alright, so let's take that, multiply it by 0.0497.
I got 0.1008, like the answer.
0.1006.
Oh, I got 0.1008.
Okay,
Mhm.
good enough. That's because you probably typed in the E, huh?
Yeah,
Don't stop typing the E in.
no, like.
Sounds right,
that's-
0.0498.
So stop typing the E, just press the E.
Yeah,
Okay.
press the E.
Okay. Alright, so we got we got 1006, okay? 8 or whatever. Same thing, alright, close enough. We're gonna drop that, alright? Okay, so it's the same thing going down the line, alright? Here, the second question is, what's the probability of there being two X being less than or equal to 2 visits, right? So again, you have to cumulatively get that, right? The probability of 0 equals X equals 0, probability of X equals 1, probability of X equals 2, right? So the probability of this being less is 0.233, but you have to calculate each one of these using the formula, and then you add them. Okay? So the best thing is to lay out your variables, then calculate the probability for each one individually, independently, and after that you can do what you need to do, okay? All right, we're not gonna go over the hypergeometric thing, because it's just a lot of math, but it's basically a lot of factorial. All right? But you use this hypergeometric distribution when you do something called without replacement, okay? So if you're doing research, you have with replacement, without replacement. Or you're doing an event, right? So let's just say I have, I got, two coins, whatever, all right? And I flip both coins or I shake let's just say I have a bag and I put everybody's name in it, all right? I shake the hat up and I say, pick one, all right? You pick one. And I tell you, hey, put your name back in, all right? That's with replacement. That means I'm putting it back in. That means that the probability of you getting selected again goes back to the same. It stays even, right? But let's just say you pick one, all right? And I do without replacement. I tell you, don't put it back, just keep it, right? What happens is the probability now has changed. The chances of someone else picking out whatever ticket or stub has now increased or decreased, whatever the case may be, right? So let's just say, well, there's 5 of us here, right? I think it's 1 out of 5 when we are picking out the little tags, right? But if I do without replacement, what does it become now?
Still 5.
No.
Or
4. Because now there's only 4 possible outcomes, right? And that's what this does. It helps you figure that out, okay? When you have without replacement. So I'm gonna go back to Vegas because they use this all the time. This is what they use to defeat or mess with card counters, right?
The FBI is gonna come to your.
Back in the day, when cards first started, saloons, Western, whatever, it was 1 deck, all right? 52 cards. It was very easy for someone to figure out what the chance of me getting the next card that I need or not, depending on how many players there were, right? And how many cards were dished out based on the game. Well, Vegas doesn't do it like that, right? Vegas, what they do is they could have a 5 deck, 6 deck, right? So what happens is you never really know what your chances are of getting the cards you need because there's so many kings in there. There's so many 7s in there. There's so many what you call this in there, right? So that makes it difficult to count the cards, right? But what they do is they take 1 card out, right? So all the cards that are out are out. So if they're using, let's just say using 2 decks, right? That's 104 cards. You get a king, you get a king, you get a king, you get a king. That's 4 kings out the door. So I already know there's 4 kings out of the possible 8 gone, right? And so that's without replacement. That helps me able to calculate the odds of me getting another king because I know there's 4 kings left, all right? Out of whatever, how many cards there are now, all right? So that helps me figure out what's the chance of me getting that card that I need, all right? So that's what you use the hypergeometric for. But again, this is not something that you use on a regular basis, and this is definitely something you put into the computer, right? Or software, because you don't want to mess with this. Okay? You don't want to mess with that. Okay? And all this is saying is like, take the factorial of 2, divided by the factorial of 1, multiplied by the factorial of 20 minus 2, divided by the factorial of 5 minus 1, divided by the factorial of 20, divided by factorial of 5.
That's a
Okay.
lot of work.
It's a lot of work. All right. So this is one of the areas where they didn't even do all the work. They skipped everything. Okay. This is one of the things where you're gonna go to the computer and basically put it in. Okay. So when it's gonna ask you for the parameters, right? The parameters are the X, the N, the S, the N, and the 0. Failure, success. Okay. The number of things you're looking for, the total number of attempts or events, right? What is this? This the space? No, that's the what is that thing? Dang it, can't remember. Yeah, number of ways to select, that's right. And then this is the N, okay? And it's capital because it's just for population, right? but not really a big deal. Okay, population, sample. Okay. All right. Lot of stuff, but I'm glad we got through it. All right. Again, formulas. All right. Don't let the math throw you off. It's just algebra and a bunch of keystrokes. You just gotta know his keystroke and how to do it, all right? I would advise you, if you're not familiar, not too comfortable with the keystrokes, go to computer, go to Google, just punch it in. What is 5 factorial? What is e to the negative third power? It'll give it to you. Okay? So, if you want to do it that way. I left a cheat sheet for you guys to study from, just to kind of look at the general concept of the questions, all right? Case studies coming up too, right? So make sure you're talking to your group members and consulting and figuring out what y'all gonna do about division of labor and that kind of thing. All right. And I'll see you guys next week.
Or the midterm is December,
Midterm is due Sunday.
and it's 15 MCQs.
Yes. What? Okay. What's up? Oh, yeah. Thanks, sir. Thank you. Yeah.
We open the quiz so I can take it, please? I
Come
took it-
see me,
At the end of the class.
and it's this session.
Oh, okay,
Come see
okay.
me week 7.
Okay, week
I
7.
gotta write my
Yes.
attendance.
Okay, thank you.
I got you. Bye.
Bye.
I got you.
The traffic is bad, Professor.
Yeah, I can
thought it was
imagine.
up north, and I was getting my tires changed, so I was,
Sorry.
yeah.